Hello everyone and welcome to another video. Today I would like to continue our discussion relating pole locations and system performance and take a look at a specific example of how to design a controller that's going to meet specific performance requirements. So the picture that went along with this, if you remember last time we drew this box here, and we said the idea with this box here is on the left side here, a manager might come over and specify performance requirements of your system. These might be things like percent overshoot, settling time, etc., whatnot, right? And the point of this box here was to translate these high-level requirements to pole locations effectively, right? These would be things like engineering specifications, right? So out the other end here, we said that those performance requirements were going to place some kind of restriction here on the requirements of the pole locations, right? And we said that the way we're going to translate between these two is the first thing that we were going to do here was we were going to do time domain analysis. Right? This was also known as performance metrics. Right? And basically what that did is it allowed us to translate between these percent overshoot, settling time, those performance requirements, and those we saw place some kind of restriction or a requirement on zeta and omega n here, right? And once we had the understanding of what did zeta and omega n have to be, we then took it one step further with actually another video here where we looked at the relationship between zeta and omega n and pole locations. Right? And that allowed us to specify where the pole locations needed to be in order to satisfy these performance metrics here, right? So the last box that we need to look at here today is that, okay, once we have these requirements on the pole locations, we can finally be in a position here to do control design. Right? Because now what we can do is we can make a controller that is going to put the closed loop poles of the system at these desired locations here and basically spit out a controller that satisfies performance requirements, right? So this was the overall picture here, and just to refresh your memory, right, this first box here, right, where we talked about translating between performance requirements and requirements on zeta and omega n, we covered that in a previous video, this one right here, right, which was entitled Deriving Percent Overshoot, Settling Time, and Other Performance Metrics for a Second Order System, right? This second box over here where we looked at how to relate zeta and omega n to pole locations, we also covered that in another video, this one over here. This one was entitled Relationship Between Poles and Performance of a Dynamic System. So the scope of our discussion today now is I would like to go through an example of this very last box here of how can we use this information we developed in these previous two videos here to finally design a controller that is going to meet these performance requirements. Okay, so let's jump into that here. Okay, so I've erased the board here, and we're going to consider the exact same example we did in the previous video here. Namely, the percent overshoot requirement was desired to be less than 20% here. We said that the settling time had to be less than 10 seconds to within delta equals 10% here of the final value here. And we needed a oscillation frequency of less than 0.1 rads per second here, right? And in the last video, we saw that these translated into restrictions on the locations of the poles here, right? So this percent overshoot requirement, we saw that that meant that the poles needed to be on some line with angle of, say, theta, let's call it theta required, right? Of 62.9 degrees here or less, right? This settling time requirement basically was a restriction on the real part of the pole here, or sigma, what we called it here, and this had to be something like 0.23, I think is what we showed in the last video. And finally, this oscillation frequency was a restriction on the imaginary part of the pole, right? And we said that in this case, this has to be 0.1 or less, right? So the picture that graphically went along with this here is we said that, all right, in the real imaginary axis, right, that all of these we were able to quickly sketch out admissible locations here, right? So here was our 62.9 degrees here. There was another requirement right here, I think of the sigma of negative 0.23 here. Find this omega d requirement was something like this, right? Here at 0.1 here, right? And all of this other region outside was inadmissible, right? So all of this is inadmissible. I want to make sure I kind of sketch this accurately. Yeah, right? All this is unallowed. So the only thing that's legal here is you better make sure that your poles end up in this white space over here, right? So at this point, if you think about this long enough, right, we actually haven't ever specified a plant, right? All we've talked about that is if you happen to have some plant here, and you happen to have some controller combination, it better have closed loop poles in this white space here, right? So at this point, if we want to design a specific controller for a specific plant, we better choose something here. So let's consider a plant that looks something like, I don't know, how about G of S is equal to S plus 0.2 all over S squared plus 0.01 S plus 0.0025, right? Let's just say that this is my plant model here, all right? Okay, so we should now ask ourselves here, the first thing you should probably do, right, when somebody drops a plant model in your lap here, along with some performance requirements, right, what's that famous phrase, right? If it ain't broke, don't fix it here, right? Maybe this system already has those, that performance, and we actually don't need to do anything. Our job would be super easy. So what I would suggest doing now is let's run over to MATLAB Simulink here, make ourselves this G of S plant here, and just input a step function and read the response, right? Stick this into a scope of some sort. And let's just observe the signal here and see, does the output, does this system already behave according to what we need it to be? If so, we're basically done, and this will be one of the shortest videos I've ever done. All right, so let's jump over to MATLAB Simulink.
All right, so I've just started myself a little script here where we can go ahead and let's first go ahead and define the plant. How about? So according to our transfer function that we're looking at here, I think this is an appropriate numerator for it, and this is an appropriate denominator. I think it was S squared plus what, 0.01 S plus 0.0025. So there we go. Here's our transfer function now. And you know what we may want to do is let's go ahead and evaluate the open loop response. Because like we said earlier, we're checking to see if this works right out of the gate, and if so, we're done. So let's just go ahead and say step G, and if we run this, we'll see how this open loop transfer function does by itself. And let me bring it over here in this main window, and if you look at this, this is ridiculous here, right? Look at this plant here. Look at the amount of overshoot. It almost looks like 100% overshoot to me, and settling time is horrendous, 600 seconds or something like this. So clearly the plant by itself does not meet the performance requirements, so we need to think about adding a controller to this thing.
All right, so that was a disaster, right? That plant by itself is ridiculous, right? It's got horrible oscillations. It takes forever to settle here. So by itself, this plant is non-compliant, right? In the sense that you put in some kind of input here, the output, this does not match the performance requirements that we need here. So to fix this thing's problem, what we're going to do is let's suggest adding a controller to this system, some C of S. Well, actually, maybe let's write this underneath of this. I don't want, actually, let's not call it C of S. Let's just call it controller. Right? And now what we're going to do is we're going to propose this type of an architecture like such. Right? So now I have some Y desired here, and now what we're going to hope is that the whole the closed loop system will now satisfy those performance requirements, right? So the question now becomes here is, what type of controller do we want to consider here, right? You could put a lead lag, a PID, a full state, something like that, something complicated. But to keep our discussion simple and just to illustrate how we can combine this with the performance metric analysis that we did earlier, let's choose a really simple, just a simple proportional controller. So in other words, I'm going to just say that this controller is just a simple gain of magnitude K here, right? Okay, so if I have that, one thing that you may want to do now is ask yourself the question here of where do the closed loop poles of the system go as K changes? So let's just write that down as an important question, right? Where do closed loop poles go as K varies, right? So hopefully what's setting off some bells in your head right now is this is a great problem for root locus, right? This is the definition of root locus, right? Root locus literally says where are all the locus or locations of the roots as some parameter in our system changes. In fact, this is the classical root locus problem here. If you'd like to see more discussion on root locus here, again, shameless plug for one of the other videos. This video over here discusses how to draw the root locus, introduction to root locus, how to sketch it by hand, how to get some tools in MATLAB to do that. So if you'd like, or if you haven't seen it already, please check this one out first, because what I'd like to do right now is just actually use material we built off in that lecture here. Namely, I'm going to go ahead and just use the rlocus command in MATLAB to have MATLAB go and solve this closed loop characteristic equation, find the roots, find the poles, all that kind of stuff, and have it vary K for me, and I can see where do all the poles go as we change the gain K. Okay, so why don't we jump over to MATLAB here and see what the root locus looks like.
All right, so in MATLAB, this is actually pretty simple. We would like to now go ahead and use our locus to draw the root locus of the system here, right? So all I need to do here is let's just start a new figure here, and I'll just say R locus of G. And let's actually turn the grid on, because that's actually going to be helpful in a second. So again, let's just run this guy and give it a second here to plot up the root locus, and I'll bring it over here so we can take a look at it. I'll blow this up. So here's apparently where the root locus is. So again, you see the two open loop poles here. And then as we increase the gain K here, you see that the roots come together in this circle, they meet on the real axis, and then one splits off this way, and one splits off to negative infinity here. Okay, so this gives us a rough idea, and where the poles are, we can now think about combining that with where are they allowed to go in order to meet the performance requirements.
Okay, this is awesome. Now we're really trucking, because we saw now in the root locus of this from the rlocus command, looks something like, I don't know, you got some poles here and here, right? And then what these two do is they kind of make this circle-ish thing and kind of meet. I'm really roughly sketching this here. And then they kind of go this way. One of them comes here, and then the other one goes that way, right? So that's what the root locus looks like. So if you think about this long enough, what we now want to do here is actually superimpose over this root locus the admissible regions of the plane here, right? So we saw earlier here, and I'm going to sketch this and probably do a bit of a bad job here, but I think everyone knows what I'm trying to draw here, right? So here was our percent overshoot requirement, right? This was our 62.9 degree angle here. There was also this other restriction, I believe, on sigma here. So we had this other one where this was at, I think, minus 0.23 here. So this was our settling time restriction. And finally, we had things like the damped natural frequency, right? Had better be something like, I'm trying to make sure I draw this accurately, something like this here at 0.1 here. So here was our omega D requirement, right? So now, with this picture, doesn't this look really interesting? Because what you can see now is, okay, you have to end up in this region, right? This rectangular region is what we were talking about. So the game plan now is find the value of K that is going to push the root locus just far enough so that it enters a region of the complex plane which simultaneously satisfies all three of these requirements. So we can kind of see just from this picture here that it's probably going to be this location right here. Let me circle it. Let me put it in red here. So we want to put the poles right there here, right? So what I want to do now is actually, let's jump back over to MATLAB, because we'll see there are actually some really helpful tools to help us find this value here. I mean, sure, you could probably do it analytically if you want, but one of the benefits of having a tool like MATLAB is you can bring a lot of tools to bear on this type of problem. And my artistry is not that good, and I'm sure it would be better if we were able to plot all of this in MATLAB to see exactly what the picture looks like, rather than me just sketching it conceptually on the board. So let's jump back over to MATLAB one more time here and find a value that seems to work for us.
All right, so tell you what, why don't we go ahead and actually, let's dock this figure here in the plot so we can see what this looks like simultaneously. Okay, and now what we want to do, like we said earlier, is we want to draw the pole constraints on our locus plot. So in other words, we want to draw those lines here and all that kind of stuff. So let's first come up here and hold on to the figure, okay? And now let's go ahead and draw the settling time requirement, right? And I think that we said the sigma required was 0.23, right? That's what we got. So what I want to do here is let's just draw, how about a red line, a red vertical line at sigma required here. So I guess I have to do minus sigma required and minus sigma required. That's the x locations here, right? And then the y locations, I wanted to go from the bottom of the plot to the top to make it look nice. So just looking at this, I think I need to go from minus 0.25 to positive 0.25. And let's make this a red line here. Well, let's make this a little bit thicker. 3, how about? That looks pretty reasonable. So let's just see if this looks reasonable here. I'll run this again here, and maybe it's come back here and redock the plot. Here we go. So here's our sigma required line, or my settling time requirement. So anything to the left of this line will meet the settling time requirements. Let's go ahead and now do the same thing. How about for omega d? Requirement, right? So I think we said that the omega d required was 0.1 or less, right? So let's draw ourselves two horizontal lines which represent that omega d requirement. So I think I need to do something like the x values need to run from, again, the negative value here of minus 0.08 all the way up to, you know what, let's just, let's go up to 0.1, that's fine. So I need to go from minus 0.8 to positive 0.1 here, and the y values here are omega d required, right? Something like that. And let's draw this as a green line, how about? And we'll, again, make it a little bit thicker. Okay, and actually, you know what? Let's draw two of them. Let's draw one at positive omega d, and we'll make the other one here at minus omega d, just so we can see the two. Again, the root locus should be symmetrical over the x-axis, so this really is just to make it look pretty. One of them should have been sufficient. Okay, finally, let's do the percent overshoot requirement, right? And I think we saw that put a restriction on theta, right? The angle was something like 62.87, or so I think, let's call it 62.9 degrees. Let's turn that into radians here. Okay, and now, again, what I would like to draw now is I want to draw an angle or a line going from the origin over here up at 62.9 degrees here. So I think you'll agree that I could do something like this. Like I could say plot, let's look at the x values going from minus 0.8 to 0. Those are the x values, and the associated y values should be what it should be. It should be positive tangent of theta required times the run, which was 0.8, something like that. That should get me that. And then obviously the one that corresponds to x equals 0 should be at y equals 0, so that should be fine. And again, let's draw this as a blue line, how about? And make it a little bit thicker. Sorry, 3. And let me see. Yeah, and actually, again, this is going to draw me this vertical line here, or the upward shooting line, but we can also make the symmetric one going down here. So that should be here at minus theta. Okay, and great. Now, if I save all this and run it, and I'll bring up my plot, and here we go. Let's go ahead and dock that in the editor here, and we see that, here we go. This looks pretty darn great, because if you look at this, we've got the root locus kind of here in the back, and then simultaneously, I mean, it took us a little bit of effort to manually draw all these lines on the same plot, but this this works. So what we can easily see here, and what's really cool about the rlocus command here, is that I actually just click on the root locus, like right here, and hold. You see that I actually get a little arrow or a little cursor that I can drag around here. So we see down here, this is the open loop polls. I got a horrible response, right? We saw earlier that was that 600 seconds of settling time, and it was just ridiculous. But as I start increasing the gain K here, right, you can see that value gain going up. That's actually row number 2 of this little box. It says something like gain. So here we are. Here's a gain of 0.256 here, right? And we see at 0.256, you know, we are satisfying the percent overshoot requirement because we're to the left of that blue line, but we're failing in both the settling time as well as the oscillation frequency requirement. So we need to keep pushing this. We need to keep pushing until right here when we hit the red line. Now at a gain of I don't know, something like this, 0.45-ish, it looks like to me. At that point, we are now satisfying both settling time and percent overshoot simultaneously, but we haven't pushed it hard enough to get the oscillation frequency working. So we're going to keep going, all the way down to here. Something like that. A gain of 0.74, right? You can see that right here. At a gain of 0.74, now I'm in the clear. I should satisfy all 3 requirements simultaneously. So let's save that in the back of our head. In fact, you know what we should maybe do here is maybe down here in our MATLAB script here, we're going to say choose/design controller to meet requirements. And we see that that is just a gain of K of equal to 0.4. So now, you know what? Let's actually start up Simulink here. And let's simulate to see if this actually will work. So we claim that this controller of K of 0.74 is going to solve all my problems here, right? So let's go ahead and I'm going to grab myself a blank Simulink model, which is right here. And let's just quickly build a system that represents the thing that we're looking at. So first of all, let me grab here a transfer function block here. And let's go ahead and put this, I think it was numerator and denominator, right? We already defined those 2 variables. So now let's go ahead and just make ourselves a step input here. So first, let's go ahead and just triple check to make sure that the open loop plant does not do what we want. So let me go ahead and put a scope on the other end here. And let's do this and maybe, whoops, sorry. Let me make this a little bit bigger here just so we can zoom in a little bit more. Okay. There we go. I don't need that hint. Okay, so great. If we go ahead and, for giggles, let's go ahead and save this thing here. I'll call it maybe a root locus model. Okay, so now if I go ahead and just run this guy, and actually this is probably not long enough. We're probably going to need to send this here to, I don't know, how about 700 seconds here of simulation time. And if we run this, again, this is the open loop plant here, right? And if we look at the associated scope here, let me just grab it and drag it onto the screen. We see horrible performance, right? Okay, so this is clearly not satisfying the performance requirements, so let's go ahead and add our controller here. So I'm going to go grab myself a gain here, and this gain is going to have a value of K, that 0.74 that we just designed here, right? So this is now my, come on, let me fix this. Come on. There we go. This is my controller. All right, and we're going to plug that into the plant over here, and we'll go grab ourselves, whoops, that's not what I wanted. I want a summing block, and let's connect these guys up appropriately. And I would like a minus sign down here instead. Great, and then I'm going to feed this back using our classical control architecture. So now what we claim is this closed loop plant should satisfy, right? Because this closed loop controller corresponds to the root locus we just designed over here. So if we run this system now, whoops, oh, sorry, you know what? This gain K is not yet defined here because I think I didn't actually run the MATLAB script here. Yeah, so the variable K is not in the workspace. So tell you what, let's run this thing one more time here. So let's come here to editor, run. Great, now K here is defined. Let me just redock our picture right there and grab our Simulink model. Where is it? Here it is. And let's look at the scope here. Again, this is the open loop response. Okay, here we go. Now we're cooking. Hit run here, and wha-bam! Look at that. We are in business here. So in fact, 700 seconds is now way too long. Let's look at just, I don't know, 30 seconds here. Run this thing again. There, this is looking beautiful. So look at this. We have 10 seconds or less of settling time. The oscillation frequencies work. The percent overshoot matches the requirements. So, yay! I think this is going to work for us and validates here. This simulation here has validated our analysis and our control design and shown that it actually does satisfy the performance requirements that we set out.
Great, so we saw that worked. At this point, I think we have a really good workflow for discussing maybe just the general theory and concept of how we can design a controller to meet specific performance requirements. So we saw here that, well, what usually happens here is that these system performance requirements will dictate pole locations, right? And based on these pole locations, that's going to drive our system design, right? So we can say that acceptable pole locations drive controller design. Once you have this candidate controller here, we can go ahead and test that either in simulation or hardware, right? So this control design is tested, right, in sim or hardware. And these results of this simulation or the hardware test will basically validate these original system performance requirements, right? So I'll say testing results validate performance requirements, right? So really, you can think about this as going around in this iterative circle here, right? Where we have these system performance requirements, right? And we said that these will go ahead and drive acceptable pole locations. Which in turn drives the control design. And this control design can then be tested here. So we can do testing and validation, which will basically show that you satisfy these system performance requirements or not. And if you don't here, you just go around and around in this circle and iterate on your control design here or your acceptable pole locations here until you get a system which does in fact satisfy these performance requirements. So I think this was hopefully an insightful, illuminating discussion here. One thing that's interesting to talk about now that we've seen sort of the whole pipeline of this here is, one thing to note here is that the previous method here where we actually had to manually draw the acceptable pole locations in the regions of space which would satisfy multiple performance objectives simultaneously, that was actually a little bit cumbersome here. So again, more shameless plugging here. This video over here is one of our other ones where we discuss something in MATLAB called CISO tool that is going to help us do those regions in space automatically here. The other thing that's kind of interesting if you think about this is this example we use might be a little bit unsatisfying because it was such a simple controller, right? It was a simple proportional control was all that we were doing here. You might ask, could I still use this technique here for something more complicated? And the answer is absolutely yes. In fact, this video over here talks a little bit about using this method here and using CISO tool that we talked about here to design more complicated controllers such as full-on proportional integral derivative or PID controllers. So, with that being said, I hope you enjoyed the video today. If so, please subscribe to the channel here because we will have lots more discussion on control theory and other tools in MATLAB to assist with aforementioned control theory in the future. So, with that being said, I hope to catch you at a future video. Bye!